If you've ever been to the American Midwest and you're anything like me, you probably looked around and thought, wow, this is flat. Like, really flat. And boring. And also it's very, very, very flat. And pretty boring, and also extremely flat. And boring, and flat, and also boring. I lived in Nebraska for about 2.5 years, and I don't think that there was a day that went by when that wasn't the first thing that went through my head when I woke up and saw the cornfield out the back window. However, I am also a nerd, and so the very next thing that went through my mind was usually, you know what? If we ever wanted to build a tangent plane to the Earth's surface, this would be the place to do it. And with the vast expanse of ski resortless land that is the Midwest, building a humongous ski ramp right down the center of it just makes all the sense in the world. Clearly my logic is infallible and you are unable to argue with it. So, what would it be like to ski down a ramp that is tangential to the Earth's surface? Here is the Earth, here is the unrealistically oversized ski ramp, and the even more unrealistically oversized skier. Let's just call him Steven for the sake of argument. Now, Steven, of course, is going to be experiencing the pull due to gravity perpendicular to the Earth's surface, no matter where he is on this ramp. However, assuming that the ramp is structurally stable, only the component that is parallel to the ramp will be doing any work on him. That, of course, can be given by his overall acceleration due to gravity multiplied by the cosine of that angle down there. So we gotta find an expression for that angle based on his distance from the center of the ramp. If you notice, we can actually draw this nice little right triangle here, and that angle there will be the same as the angle that we are looking for. Well, if one leg of the right triangle is his position along the ramp, and the other one is just the radius of the Earth, right? So we can go ahead and figure out our angle in terms of the radius of the Earth and his position along the ramp. Alright, sweet. Well, now we've got an expression to describe the horizontal force of gravity at different points along the ramp. Seems easy enough. Almost seemed too easy. You know what? We forgot to take into account the fact that gravity changes with distance. And I mean, this is a pretty long ramp, so maybe we ought to throw that in there too. Shouldn't be too difficult. I mean, we already got this. That just means that the distance from his center of mass to the Earth's center of mass is going to be, well, square root of r squared plus x squared. Easy peasy Pythagorean stuff, right? Sweet. Well, then that means that the horizontal component of the gravity should just be gravitational constant times the mass of the Earth times the mass of the skier divided by the distance squared, and then times the whole angle stuff that we did earlier. It's a little bit more complicated, but it's still manageable. It almost feels too manageable. You know what? There's going to be some friction tugging on him in the opposite direction. Okay, well, friction depends on the normal force, and the normal force is just going to be pointing directly up to counteract the gravity in the y direction, so normal force should be the same thing as gravity in the x direction, except you're going to use a sine instead of a cosine right there. And then you just multiply that normal force by the coefficient of friction, and you're all good. You got your friction done. Well, actually, I suppose that air resistance is, in fact, a type of friction, so maybe we should take that into account as well. This right here gives you the magnitude of the drag force, and if you, instead of velocity squared, use velocity times the absolute value of velocity, then that preserves direction. And, well, there we go. That's all of our forces. Well, actually, I suppose that the density of air actually changes as you go higher up in the atmosphere. We probably need to account for that. Well, we already talked about the height above the Earth's surface, so we already have an expression for the height, which is nice. So then that means that we need to use this expression for the density of the air, and we'll go ahead and just plug that back into the drag equation, and there we go. It's looking a little bit complicated now, but that's okay. Now we can just say the net force is going to be the sum of all these, right? Positive gravity, negative friction, negative air resistance. It's fantastic. And then we can actually multiply this whole thing by the reciprocal of the mass, and then we'll have the acceleration, which, I mean, that's really just the second time derivative of the position function, and the velocity is also a time derivative of the position function. And speaking of functions, the pressure function that we were looking at earlier, that's technically a piecewise function, because the atmosphere doesn't behave the same way at all elevations, so maybe we need to account for the fact that this is a piecewise function. And, well, I mean, if we're making this ramp really, really long, like way out into space, then we might want to account for the gravitational pull of the moon, but, you know, that's going to be changing as it goes around Earth, and Earth is spinning, so the gravitational is going to be changing all the time. And you know, the Earth is spinning pretty fast, and like if we have just a stiff board way out there, I mean, that's going to be some pretty high tangential velocity. Maybe we need to take into account some special relativity stuff. And, well, that's not even to mention the intense solar winds of the sun. That's going to exert some force on him, you know. And I mean, who's to say that he's even right there anyways, you know? I mean, once you start learning quantum mechanics, it all goes out the window. Maybe we need to find his wave function to really get this down, but, you know, it's going to be depending on time, so we should find his time-dependent wave function. And then what about the...
Has this ever happened to you? Every single year, thousands upon thousands of physics and engineering students all across the globe subject themselves to intense anxiety and panic attacks as they realize that there are always more factors to be accounted for. No one has ever solved a physics problem that matched the real world 100%. Everything in physics is a spherical cow. Some cows are more spherical than others, yes, but they are at the end of the day ultimately spherical cows. So, when you're making a video about something as ridiculous as a ski ramp to space, don't be afraid to make it as spherical as you want.
Huh. Well, that was weird, but thanks, Mr. Disembodied Floating Voice. You're right, I can make this as spherical as I want. And this is as spherical as I want. No drag, no friction, just good old gravity. So if this is the only force that we're accounting for in this admittedly very, very ridiculous problem, well, we can go ahead and divide out the mass of the skier and find the acceleration. It might be a little bit weird to see acceleration as a function of position here, as opposed to time, but this is what it looks like when you plot it. You're actually going to be experiencing zero acceleration right at the center of the ramp, where it's tangential to Earth's surface, which is what we would expect since you're basically just standing there. You'll experience the greatest acceleration of about 3.77 meters per second squared, 4,500 kilometers away from the center of the ramp. If we decided to start building this ramp at the geographic center of the continental United States and just kept on building north, your location of greatest acceleration would be at an altitude of about 1,400 kilometers, right above this island in Canada. After hitting that peak right there, your acceleration tapers off pretty quickly the farther along the ramp you go, but of course, acceleration is not the same as speed or position. Acceleration is just the second time derivative of position, after all, which means that we got ourselves a differential equation. And technically there are several different variables in this differential equation, which means that it's time for some multivariable calculus. Some calculus? Multivariable calculus? Now, you technically don't really need any multivariable calc skills to do this. I just really wanted to use that somewhere, so... Anyways, one quick separation of variables later, and we can throw this over to Mathematica to integrate it, throw this on the other side of an equal sign from the time integral, and solve for x. So, Euler's method works by approximating very small segments of your curve as just linear, and then you can use kinematics to work through it all. Then just let a computer do this for you a couple thousand times, and you can plot Stephen's trajectory along this massive ski ramp. And I mean, you get some interesting shapes for sure. Like with this velocity graph, you can definitely see that you blow past the center of the ramp and then you start slowing down until eventually you turn back around again. And well, I'll be honest with you, I really have no idea where this video was going. I had the idea a couple of months ago, and I thought that it would be a cool video to make, you know, a ski ramp to space, but I honestly have like no idea what the point of the video is. Maybe you can tell me what the point of this video is down in the comments or something. Tell me, what did you learn today? I learned that I should have a more structured plan before setting out to make a video like this. But if you made it this far, thanks for watching anyways. My odd sense of humor and my odd fascination with math and physics. If you liked it, then maybe you should check out some of these end screen videos or something, I guess.